Organizations are currently dismantling monolithic AI applications. They are replacing massive centralized models with networks of autonomous agents that interact and operate independently. When enterprise architects look at this shift, their instinct is to apply a familiar logic: microservices. In software engineering, the rule has long been to decompose monoliths into smaller pieces. One service, one responsibility. The boundary is the feature. This comparison illustrates the trap. On the left, we have standard microservices. On the right, an agentic AI network. They look like similar structural decompositions, but they solve different problems. Microservices decompose strictly for deployment. Breaking an application into distinct blocks optimizes for operational flexibility and scale. You isolate services so you can update or duplicate one without breaking the rest. Agentic AI decomposition addresses a different constraint. In these systems, strict boundaries are required to make runtime governance possible. The cost of failure reveals the difference. If a microservice handles too many features, it creates operational friction. But if an AI agent operating at machine speed handles too many powers, it becomes an active, compounding liability. Safe agentic architecture requires a different structural commitment to keep agents auditable and controllable as they scale. This principle is called atomicity. To understand atomicity, we must first define what it actually takes to govern an autonomous agent while it is running. Look at this structure. This is a kitchen sink agent. It takes in raw data, analyzes it, decides on a course of action, and executes it. It is highly capable, but it is effectively ungovernable. Governance relies on policy as data. This is the practice of attaching executable governance rules directly to an agent at runtime, rather than writing static procedures to be reviewed after the fact. When an agent analyzes data and then makes a decision based on that analysis, policy binding fails. The rules governing evidence production are different from the rules governing decision authority. By collapsing them into one agent, you force conflicting rule sets onto a single actor. Your policy becomes an imprecise compromise. The second pressure of governance is the blast radius. Autonomous agents experience behavioral drift. Over time, as inputs and feedback loops shift, an agent's actions will deviate from its original alignment. When an atomic agent drifts, you can isolate and roll it back. But when a multi-purpose kitchen sink agent drifts, the error is distributed across everything it touches. You cannot isolate the analysis from the execution. The final pressure is auditability. Risk functions and regulators demand a clean event trail, a precise record of what an agent perceived, what constraint it evaluated, and what action it took. A multi-power agent conflates evidence production with decision authority. The same mechanism that generated the analysis also authorized the action. The resulting event trail ceases to be a clear historical record and becomes a forensic challenge. Policy binding, blast radius containment, and auditability all depend on structural isolation. When an agent takes on multiple powers, these governance mechanisms become imprecise and harder to enforce. Escaping the kitchen sink model requires a strict definition of boundaries. This is where atomicity provides a hard architectural constraint. What you are looking at here are the three parameters of an atomic agent. The first is one power. Power is the explicit type of authority an agent holds. Analyzing is a power. Planning is a power. Approving is a power. The second parameter is one scope. This is the specific domain the agent operates within. A pricing agent scoped to a single product tier in a single region has one scope. If it begins pricing across regions with different regulations, it requires a different rulebook. The third is one objective. The agent optimizes for a single declared outcome. If an agent is silently balancing cost reduction against customer fairness, it is making implicit trade-off decisions. That trade-off belongs in a higher-level policy, not hidden inside the agent.
You can identify violations of these three parameters in a design review with zero tooling. You just use the AND test. If an agent's description contains AND, split the role. Let's apply this to a common engineering pattern, an agent designed to verify compliance and approve action. Verification exists to check approval. If the same agent performs both functions, it is checking its own work and authorizing itself to proceed. It eliminates the independent control that makes verification effective. The resolution is architectural. You draw a hard boundary, name the two distinct powers, build two separate agents, and force a strict data handoff between them. That handoff between the verifier and the approver is not system overhead. That handoff is the location where governance happens. Atomicity violations rarely cause immediate crashes. They accumulate quietly during development, only revealing themselves during a compliance audit or a sudden scaling event. The most common failure mode is the accumulating agent. It starts with a single purpose, but as the system evolves, it absorbs adjacent functions. Engineering teams do this because it feels pragmatic. Adding a behavior to an existing agent is faster than introducing a new one and establishing a handoff. The consequence is an unmanageable blast radius. When the accumulator fails, no one can isolate the specific function that drifted. Fixing it requires taking down the entire operational surface. The second failure mode is the super orchestrator. This is designed as a master agent that coordinates downstream agents while also holding decision authority over them. Teams build this under the logic that a single agent needs to see the whole picture to direct traffic. But sequencing tasks is different from decision-making. A super orchestrator acts as both the traffic controller and the judge. It authorizes its own paths, bypassing independent governance checkpoints. The third mode is the self-contained pipeline. Raw data goes in, the agent processes it, makes a judgment, and outputs a final decision. Internally, it is executing multiple powers sequentially. But it does this without policy gates or observable intermediate states. Because no intermediate steps produce observable events, auditing the agent requires auditing the entire pipeline simultaneously. At scale, this leads to compliance failure. Accumulators, orchestrators, and pipelines share the same flaw. They hide multiple distinct authorities behind a single boundary, making external oversight impossible. When strict atomicity is mandated, engineering teams often push back. The concern is that atomicity will result in an infinite proliferation of microscopic agents, causing the system to drown in coordination overhead. But atomicity is not about minimizing the line count of your code. An agent can be complex internally. The goal is to make governance boundaries explicit. To find a right granularity, architects use 4 design tests. We know scope, objective, and the AND test. The final diagnostic is the kill switch test. Can you remove an agent's power without freezing the surrounding architecture? If not, the agent is deeply entangled. And these tests also protect against overgranularity. If you split an agent into 2, but both share the exact same policy, scope, and kill switch, you have gone too far. If the separation provides no distinct governance value, they are the same agent. They should be merged. This returns us to a core requirement of agentic architecture. An agent you cannot isolate is an agent you cannot govern. In a high-speed network, one ungovernable actor never stays isolated. Its outputs immediately become inputs for downstream agents. Its behavioral drift infects the entire system. Atomicity is certainly not a design aspiration. Imposing atomicity onto an active system running with blurred scopes is not a simple refactor. It requires a complete and costly re-architecture. The solution is discipline at the blueprint phase. Draw the boundary, name the power precisely, then build the agent.